This video is on fundamental and derived units. Part 1, state the 7 fundamental units and their symbols. The fundamental units of length is meters. For mass, it's kilograms. For time, it's seconds. For current, it's amperes. For temperature, it's Kelvin. For quantity, it's moles. And for light intensity, it's candela. And here you could see the symbols. For meters, it's M. Kilograms, it's little kg. Seconds, it's little s. Amperes, it's capital A. Kelvin is capital K. Moles is little mol. And candela is capital C, little d. So memorize these two acronyms to memorize the SI fundamental units. My knuckles grow stronger and kill more creatures means meters, kilograms, seconds, amperes, kelvins, moles, candela. So here are some two notes. Kilogram is a fundamental unit, but kilometer is not. And ampere is a fundamental unit, but coulomb is not. Ampere is coulombs over seconds. Part 2, answer the following questions about fundamental units. Question number 1, what is the meaning and what are the fundamental units of perimeter? Perimeter is a total distance around a two-dimensional object, has units of meters. Question 2, what is the meaning, equation, and the fundamental units of circumference? Circumference is a total distance around a circle. The equation is 2 pi r over pi d, has units of meters. Question 3, what is the meaning and what are the fundamental units of area? Area is the total number of squares in a two-dimensional object, has units of meters squared. Question 4, what is the meaning and what are the fundamental units of volume? Volume is a total number of cubes in a three-dimensional object, has units of meters cubed. Question 5, use the equation V equals delta x over delta t to solve for the fundamental units of velocity. The fundamental units of velocity is meters over second. Question 6, use the equation A equals delta V over delta t to solve for the fundamental units of acceleration. The fundamental units of velocity have been solved for earlier in the last problem. So acceleration is defined as delta V over delta t, which has units of meters over second, which is meters over second squared. Question 7, what are the units of force? Use the equation F equals ma to solve for the fundamental units of force. The fundamental units of A have been solved for earlier. So the fundamental units of force is newtons. F equals ma. The fundamental units of mass is kilograms. And for acceleration is meters over second squared. So 1 Newton is kilograms meters over second squared. No need to memorize this, just understand the process. Question 8, use the equation F equals minus K delta X to solve for the fundamental units of the spring constant K. F sub H is the force on a spring, which is called Hooke's law, and delta X is the displacement of a spring from its equilibrium position. The fundamental units of force have been solved for earlier in the previous problem. So first solve for K. K equals minus F sub H divided by delta X. The negative sign doesn't have any units. The fundamental units of force is kilograms meters over second squared. The fundamental units of delta X, which is a change in displacement, is meters. So you get kilograms over second squared. Question 9, use the equation F sub D equals 6 pi nRV to solve for the fundamental units of the fluid viscosity eta. F sub d is the drag force on the object, r is the radius of the object, and v is the speed of the object. The fundamental units of force have been solved for earlier. The Greek letter n is pronounced eta. So it's eta. So first solve for eta, then substitute the units of each variable. You could see in the denominator 6 doesn't have any units, pi doesn't have any units, but r has units of meters, v has units of meters over seconds. Question 10. Use up equation P equals mv to solve for the fundamental units of momentum p. The fundamental units of velocity have been solved for earlier. So P equals mv, you get kilograms times meters over second. Question 11. What are the units of energy? The units of energy are joules. It's not a fundamental unit, but its units are joules. Question 12. Use the equation E sub k equals 1/2 mv squared to solve for the fundamental units of kinetic energy. M is the mass of an object and v is the speed of an object. So 1/2 is a constant. It's not a variable. It doesn't have any fundamental units. Fundamental units of mass is kilograms. Fundamental units of speed is meters over second. So all energy has the units of joules, and 1 joule is kilograms meters squared over second squared. Question 13. Use the equation E sub p equals mg delta h to solve for the fundamental units of the gravitational potential energy near the surface of a planet. G is the acceleration of an object near the surface of a planet, and delta h is the height an object is raised or lowered. The fundamental units of acceleration have been solved for earlier. So you could see the answer for 13 has units of joules because it's the units of energy. And the solution for 13 is the same as the solution for 12. Both kinetic energy and gravitational potential energy have the fundamental units of kilograms meters squared over second squared. So question 14, what are the fundamental units of energy? It's kilograms meters squared over seconds squared. Question 15, what are the units of work? The units of work is joules. And we're going to use this equation W equals Fs cosine theta to solve for the fundamental units of work. So the fundamental units of force is F equals ma, which is kilograms times meters over second squared. The fundamental units of S is displacement, which has units of meters. And cosine theta doesn't have any fundamental units. It's unitless. Question 16, what is the relationship between the fundamental units of work and energy? They have the same fundamental units. This means they have a very close relationship, work and energy. Question 17, what are the units of power? Use the equation power equals work over time to solve for the fundamental units of power. The fundamental units of work has been solved for earlier. So power is work over time. We could just look at a previous problem to plug in the fundamental units of work, which is kilograms meters squared over second squared. So now we have our solution for the fundamental units of power. Question 18, use the equation torque tau equals Rf sine theta to solve for the fundamental units of torque tau. R has units of distance and F is the external force acting on an object. Theta is the angle between R and F. So the fundamental units of R is meters. For force it's kilograms meters over second squared, and sine of theta has no units. So in the yellow highlight, torque has the same fundamental units as energy and work, which is joules, but they are not the same. So there's no direct relationship between torque and energy. So yes, work and energy have a close relationship. Work, energy, and torque do not have a close relationship, even though they have the same fundamental units. Question 19. Use the equation I equals kmr squared to solve for the fundamental units of the moment of inertia. K is a unitless constant, which depends on the physical dimensions of the object. M is the mass of the object, and R has units of distance. So the moment of inertia has fundamental units of kilograms times meters squared. When you learn about rotational motion, you'll learn more about the moment of inertia. Question 20. Use the equation delta L equals tau delta T to solve for the fundamental units of angular momentum L. The fundamental units of tau have been solved for earlier. So we plug in the variables, and this is the answer we get: kilograms meters squared over second. Question 21. Use the equation L equals I omega to solve for the fundamental units of angular speed omega. So let's solve for omega, and we've already solved for the fundamental units of L and I earlier. So the fundamental units of angular speed is 1 over s, which is very close to meters over second. Question 22. Use the equation tau equals I alpha to solve for the fundamental units of angular acceleration. So angular acceleration equals tau over moment of inertia I. We plug in those fundamental units. Our solution is 1 over second squared. So the units of angular acceleration are very close to the units of linear acceleration. Question 22. What is the equation with the fundamental units of density rho? Density is mass over volume. The fundamental units of density is kilograms over meters cubed. Question 24. Use the equation average kinetic energy equals 3/2 k sub b t to determine the fundamental units for the Boltzmann's constant k sub b. So first use that equation, solve for k sub b, and then plug in the fundamental units for E sub k and for t. So E sub k has units of energy. T has the units for temperature, which is Kelvin. Question 25. Use the equation Q equals mc delta T to determine the fundamental units for the specific heat capacity C. Q has units of energy. So we have this equation Q equals mc delta T, solve for C, plug in the fundamental units, and see what happens. Question 26. Use the equation Q equals mL sub F to determine the fundamental units for the latent heat of fusion L sub F. Q has the units of energy. So Q equals mL sub F. Solve for L sub F, plug in the fundamental units of the variables, and you see the solution. Question 27. Use the equation delta Q over delta T equals Ka delta T over delta X to determine the fundamental units for the thermal conductivity K. The variable Q has units of energy. So we have a big T, which is change in temperature, and a little t, which is change in time. So first we solve for K, then we plug in the fundamental units of each variable, and then we get a solution. Question 28. Use the equation L equals sigma AT to the fourth to solve for the fundamental units of the Stefan-Boltzmann constant sigma. L is the luminosity of an object and it has units of power. A is the surface area of an object, and T is the temperature of an object. The fundamental units of power have been solved for earlier. Remember, the first step is solve for the variable sigma. Second step is substitute the equation, the variable with its fundamental units. And then finally, solve for the fundamental units. Question 29, use the equation B equals L over 4 pi d squared to solve for the fundamental units of the apparent brightness B. L is the luminosity of an object and has units of power. D is a distance from a light source, and the fundamental units of power has been solved for earlier. Question 30, use the equation E equals P over A, power per unit area, divided by sigma T to the fourth, to solve for the fundamental units of emissivity E. So when we plug in the fundamental units of the variables and cancel everything out, we realize we have no units for emissivity. Question 31, specific energy is defined as energy transferred per unit mass. Determine the fundamental units for specific energy. And you see what we did here. Question 32, energy density is defined as energy transferred per unit volume. So it's going to be joules per meters cubed. Question 33, what are the units of pressure? Use the equation P equals F over A to solve for the fundamental units of pressure. The units of pressure is Pascal. The equation we use is force per unit area. Substitute the variables with its fundamental units to get kilograms over meters seconds squared. Question 34, use the equation PV equals nRT to solve for the fundamental units of the ideal gas constant R. So P has units of pressure, V has units of volume, R is the gas constant, and T is temperature. So first step is solve for R in the equation, and then plug in the units. And then we get the answer for the fundamental units. Question 35, use the equation S is equal to delta Q over delta T to solve for the fundamental units of entropy S. Q has units of energy. You see what's done there. Question 36, use the equation S is equal to K sub B ln omega to determine the fundamental units for the Boltzmann's constant K sub B. So first, take that equation, solve for K sub B, and then plug in the fundamental units for each variable. So omega has no units, so natural log of omega has no units. So the fundamental units of K sub B is going to have the same fundamental units as entropy S. Question 37, what are the units of current I? We're going to use the equation I is equal to delta Q over delta T to solve for the fundamental units of current. So that's going to be coulombs over second, but we know a coulomb is an amperes times second. So the fundamental units of current is amperes. So always convert coulombs to amperes times second, because coulomb is not a fundamental unit, but amperes times second is a fundamental unit. Question 38, use the equation I equals delta Q over delta T to solve for the fundamental units of charge Q. So first solve for Q. The fundamental units of charge is amperes second. So for 38, the fundamental units is not coulombs, it's amperes second. Question 39, what are the units of voltage? Use the equation V equals W over Q to solve for the fundamental units of voltage. W is the work done on a charge, and Q is the amount of charge on an object. So, W over Q, the units of work is joules. The units of charge is amperes times second. So we remember from a previous problem, the fundamental units of joules is kilograms meters squared over seconds squared. Question 40, what are the units of the resistance in a resistor R? The answer to that is ohms. Use the equation V equals IR to solve for the fundamental units of resistance R. So solve for R. R is equal to V over I. Then plug in the fundamental units of each variable to get your solution. Question 41, what are the units for the capacitance in a capacitor? So we're going to use the equation Q equals VC to solve for the fundamental units of capacitance C. The fundamental units of V and Q have been solved for earlier. So the fundamental units of capacitance is farads. C is equal to Q over V. We plug in the fundamental units for each variable and we get a solution. Question 42, what is the meaning and what are the fundamental units of period T? So we're talking about waves here. Period is a time for an object to complete one cycle or revolution, has units of seconds. Or it's a time for one wavelength to pass a fixed point, has units of seconds. Question 43, what is the meaning, what are the fundamental units of frequency F? Frequency F is the number of cycles completed every second, has units of 1 over second or hertz. Cycles is not a real unit, so no one ever says cycles is a unit or revolutions is a unit. Question 44, what is the meaning and what are the fundamental units of wavelength lambda? Lambda is the length of a wave. Question 45, intensity is defined as power per unit area. What are the fundamental units of intensity? The fundamental units of power have been solved for earlier. The fundamental units of power have been solved for earlier. So intensity is power per area, which is watts over meters squared. And we're going to substitute the fundamental units of watts. Question 46. Use the equation force of gravity equals gmm over r squared to solve for the fundamental units of the gravitational constant g. So first solve for big G. Then we're going to plug in the units. M1 is a mass of object 1, M2 is a mass of object 2. Question 47, use the equation V sub G equals Gm over R to solve for the fundamental units of the gravitational potential V sub G. So, you plug in the fundamental units and that's the solution we get. Question 48, use the equation electric force F sub E to solve for the fundamental units of the permittivity of free space E sub 0. F sub E is the electric force on an object, Q is a charge of an object, and R is the distance between the two charged objects. So first solve for E sub 0, the permittivity of free space, plug in the fundamental units for each variable. Notice 4 has no fundamental units because it's a number, it's not a variable. Pi has no fundamental units because it's a number, it's not a variable, it doesn't change. Question 49, use the equation F sub E equals KQQ over R squared to solve for the fundamental units of the Coulomb constant K. And you could see what was done there. You could see questions 48 and 49, they have almost the same fundamental units It's just flipped. You just take the inverse of one to get the other. Question 50, use the equation F sub E equals QE external to solve for the fundamental units of the electric field E. So first solve for E, then plug in the fundamental units for each variable to get an answer. Question 51, use the equation V equals KQ over R to solve for the fundamental units of the electric potential V sub E. So 51, there's a small mistake. It should say V sub E, not V sub G. You could see there's a mistake there. So plug in the fundamental units for each variable to get an answer. Question 52, what are the fundamental units of magnetic field B? That's Tesla. Then use the equation F equals QVB to solve for the fundamental units of the magnetic field B. So first solve for B, which is F equals QV. Plug in the plug in the fundamental units for each variable. Then you could simplify to get an answer. Question 53, use the equation force per unit length equals mu sub 0 I1 I2 divided by 2 pi r to solve for the fundamental units of the permeability of free space mu sub 0. So first solve for mu sub 0 and then plug in the fundamental units for each variable. Question 54, what are the units for the magnetic flux psi? Use the equation psi equals BA cosine theta to solve for the fundamental units for the magnetic flux psi. So cosine theta has no units. We've already solved for the fundamental units for magnetic field and for area. Question 55, use the equation E equals HF to solve for the fundamental units of Planck's constant H. So first solve for H, plug in the fundamental units for energy and frequency, and you get an answer. Question 56, use the equation lambda equals H over P to solve for the fundamental units of the de Broglie wavelength, lambda. And wavelength should have the units of meters because it's wavelength, and we get units of meters.